Welcome to Absolute Value and Radicals for Pre-Calculus Math 11, and we're taking a look at Simplifying Radical Expressions, sections 2.2. Really, let's diagram what a mixed radical looks like. We have a couple of pieces here. We have the coefficient, which is the piece that is sitting out front. That's the number multiplying by our radical. That's the same as any other kind of coefficient idea. We have the little number which indicates if it's a square root, cube root, and that's called the index. And we have the value that we're actually taking the root of, and that's called the radicand. So the multiplication property of a radical states that the multiplication inside a radical, so we have a radicand which is a multiplication, can be broken up into two separate radicals multiplied together. So there's two little restrictions that we're going to write down, where the n, which is the index, needs to be a member of the number set n, and n number set is natural numbers like 1, 2, 3, 4, 5, 6. And we also have that both a and b have to be real numbers. So we can use this rule to simplify radicals. Arrange the following radicals in order from least to greatest. Now, if we look at this question in 1a, we notice that the radicands are different, but the index is the same. So the best we can do here is let's think about same index. So write these as an entire radical. So an entire radical is where you get everything underneath the radical sign. So certainly 3 root 5, we could change the 3 into square root 9 times root 5. Root 27 is already an entire radical. 4 we could write as root 16 times 2. And we get root 9 times 5 is root 45, root 27, and root 32. And if we want to list these in order from least to greatest, we can go root 27, root 32, and root 45. What about when here we have in example B, we have that the index, same index, and the same radicand. So compare coefficients. So why don't you try and do this one? Hit pause and list this in order. So because negative 2 is smaller than 5 is smaller than 6, we can list this in the order negative 2, 5th root of 7, 5 and the 5th root of 7, and 6 times the 5th root of 7. And there it's written from least to greatest. Division property of radicals. Very similar to the multiplication property. The nth root of a quotient can break up into the nth root of the numerator over the nth root of the denominator. And again, we're going to write down these statements that n has to be a member of the natural number set, and a and b have to be real numbers. And more importantly, or not more importantly, but equally as importantly, b can't equal 0 because we don't want to divide by 0. Again, this doesn't really deal too much with positive or negatives, taking the square root, cube root, that sort of thing. We'll see this shortly. But let's take a look at these questions. So we want to write the cube root of negative 54 over 56 as a mixed radical. So what we're going to do is we're going to break it up, first of all, into two separate radicals, one for the numerator and one for the denominator. Because we're dealing with a cube root, our index is cube root, we want to look for perfect cubes in 54 and 56. So the perfect cubes are 8, 27, 64. We're already big there, so let's take probably 8 or 27. Cube root of 54 does break up into 27 times 2. Cube root of 56 multiplies by cube root of 8 times cube root of 7. So right now they're designed to contain some sort of cube root. So we can assume that one should work out fairly nicely. Cube root of negative 27 is negative 3. Cube root of 2. Cube root of 8 is 2. And cube root 7. And just as a final step, let's write this together. Negative 3 halves, certainly the coefficient. Cube root of 2 sevenths is what we're looking for. Writing 2/5 times root 10/3 as an entire radical. So basically going the other direction. We have a mixed radical and we want to write it as an entire radical. Why don't you try and hit pause here and see if you can do some work to figure out that answer. Okay, we need to turn the 2 and the 5 both into radicals. So let me maybe break up the 10/3 into a root 10 over root 3 first. 2 is the same as root 4. 5 is the same as root 25. Because we're talking about square root, basically we can figure out the number underneath the radical by squaring the coefficient. So we end up with root 40 and root 75, 25 times 3, which gives us, root 40 over 75 rooted, which, if you want to go through an extra step here, you could probably reduce both of those by at least 5. 40 divided by 5 is 8, and 75 divided by 5 is 15, and we still have the radical there. So root of 8 over 15 is a nice entire radical. So now we're going to get into the whole idea of us having to take positives and negatives square roots. When a number is squared, it always becomes greater than or equal to 0. So basically it becomes positive, but it could also be 0. So if we take the square root of x, it can only have a solution when x is positive. Or again, let's change that. Positive or greater or equal to 0. So let's just say when x is greater than or equal to 0. This means that the square root of x is only defined when x is greater than or equal to 0. On the other hand, the cube root of a negative number is always negative. So the cube root of a negative is negative. Cube root of a positive number is always positive. And the cube root of 0 is 0. So what happens is that we can take the cube root of any kind of number. A cube root is defined for all real values of x. So x as a part of the real number set. This kind of statement really applies to any even or odd roots. If we think about the square root, the fourth root, or the sixth root and above, we must be taking the square root of a number that is either 0 or positive. If we are taking the third root, fifth root, or seventh root and above, we can take those roots of both positive and negative values. So determine where the following radicals are undefined and simplify them. So we have to take the root of a positive number when we're talking about square root. So let's take the radical. Since 36 is always positive, we can just say that the x squared has to be positive. And since we've seen this, x squared is always positive, we can find out that x could be any real number. So as long as x is any real number, we square it first, it definitely becomes positive, and then we're okay to take the square root. Root 36 x squared breaks up into root 36 root x squared. The root of 36 is 6, and we saw in the last chapter that the square root of x squared is basically the same as absolute x. So we get 6 absolute x for our solution. Let's take a look at b. We're trying to take the cube root of a number. Again, because we were talking about the cube root, here in this case, the variable a can be any real number. So because the cube root of a negative is still negative, cube root of positive, positive, everything's fine there. We don't really have any restrictions on a. So cube root of negative 16, well, let's break that up into negative 8 times the cube root of, sorry, not 3, 2 times a. Cube root of negative 8 is negative 2, and we really don't have any simplifying we can do for the cube root of 2 or the cube root of a. So we end up with negative 2 cube root of root 2a. Cube root of 2a, sorry. Why don't you give C a try? Hit pause and see what you can do. So we need to guarantee that the variable here, which is b to the power 8, has to be bigger than or equal to 0. We can make a little statement that since b to the 8 is always positive or equal to 0, we can say that b can be any real number. And what we end up with is the fourth root of, we need to look for some perfect power 4s that fit into 81. It turns out 81 itself is a perfect fourth power. And we're multiplying that by the fourth power of, or fourth root of b to the 8. Fourth root of 81 is 3. The fourth root of b to the 8 is b squared. Now, this is actually a very similar type question to question A here, where we have 6 absolute x. Here we have 3 times b squared. You might think that we could put in an absolute around that, but because the b squared itself is guaranteed to be positive, we don't need to bother with that. And our final example, why don't you give that one a try as well? Okay, we have the fifth root. We know that when we're taking the fifth root of a number, that we can take the fifth root of both an even or odd number. So the seventh, x to the power 7 can be all real, which means that x fits into all real numbers as well. We have 3 times, we're going to take the fifth root. There must be fifth roots that fit into 96. Perfect powers of 5, 2 to the power 5 is 32. 32 does fit nicely into 96 by multiplying 32 times 3. And we also have the fifth root of x to the 7. So 3 times the fifth root of 32 is 2. Fifth root of 3 doesn't really do much for us. X to the power 7, fifth root of that, we can reduce to, let me break this up, maybe into fifth root of x to the 7, sorry, x to the 5, and fifth root of x squared. 3 times 2 is 6. The fifth root of x to the 5 just gives us an x. And we have what's left over of the fifth root of 3x squared. This ends the notes for absolute values and radicals, and simplifying radical expressions, section 2.2.